Yes, so can see if am I audible and the screen is visible. Hello. Am I audible? So let's wait for a couple of minutes when other people may join. Meanwhile, I would like to have a background of the joining students so that I can understand that how deep I can go in. So one by one, can you please mute and introduce yourself? Does anyone want to volunteer to introduce themselves? So you can speak out, right? You can unmute and speak out. That is completely fine. So the issue is that I want to make this session an interactive one, which will be beneficial for you as well as for me, because then I'll also gain some understanding, a more deep understanding on the topic. If you ask me an interesting questions, so that is the purpose. So anyone want to introduce themselves?
Yes, sir. I'm audible. Yes, sir. I'm Shivraj Babar. I'm currently studying in the fourth year of Electronics and Telecommunication Department of GSPM Rajesh Shah Punjab.
BTech student?
Yeah, BTech student. Yeah, I'm currently studying in fourth year.
Okay. So you must be
In J.
preparing for a placement, right?
Yeah. I'm now currently preparing for placements.
Okay. So I see someone has mentioned a in Rajat. Okay, nice to know. And any other person want to introduce themselves? See, if you don't make this interactive, it will be one-way communication, so that won't be good. Anyway,
Hello, sir.
yeah,
This is Prakhar Gupta. I am third year ENTC student from SIT Pune.
nice. So you are also undergrad.
Yeah, third year.
Any other person? We still have a couple of minutes.
Good evening, sir. I am Molly Chopra and I am pursuing ECE and I am in second year.
Okay. UG?
Yes, sir, UG.
Fine. So most of the students seem to be studying in undergraduate, so taking this course. So a couple of quick questions. So do you have familiarity with PN junctions or the band diagrams aspect of that? Because that will be very helpful while discussing the concepts. Else I'll need to make you understand those concepts first. So anyone who doesn't know PN junction, okay, I can assume that everyone understands PN junction to a certain depth, and about band diagrams of PN junctions and other devices, energy band diagrams. So fine, let's begin then. So this is NOC 25W110 NPTEL tutorial on electronics devices to circuits. So I am TA in this course. My name is Debashish Nandi. I am from IIT Kanpur. I am a PhD student here, and my pre-final year. The course is organized by NPTEL team, and the course instructor is Professor Sudeb Dasgupta from IIT Roorkee. He is a very senior professor in our domain. So I hope that you guys have been following the lectures. So the tutorial session is planned on every Saturday from 7 to 9. It will be a 2-hour session. I would be very happy if you can make it interactive so that ideas can exchange between us. It will be a 12-week course and probably followed by one summary session. So these are some of the prerequisites which I expect from you, that you should have been gone through the previous week's lectures, and also I expect you to you must have attempted the assignment problems or the quiz questions that is posted on the this Swayam portal, right? And also please keep your microphones and videos off during these sessions. And if you are asked to unmute, please do so. And also you can use the raise hand option so that you can be given a fair chance to ask a query. It will be a second 2-hour session, and at the end, generally this will be my fourth NPTEL TA duty. So I generally don't find time at the end of second hour, but it will make the session more interactive. But if you want to ask some query at the end, that will also be. Also, please say it will be very good that if you can do the problems simultaneously with me, so that you can pair them. Right? And this session links, I think you must not have received the link yet. If you already have, that's fine. If not, then it will be provided shared to you by the NPTEL. Okay? And also probably when it is shared, so I may also disclose the YouTube channel where these recordings will be posted. So let's begin with today's. So, so these are some of the warm-up questions that were posted on assignment 0 made call. So the purpose of this is that not to just answer the questions, to understand the underlying concepts behind each terminologies and each options. Okay. So let's start with the first question. So BJT is a 4-terminal device. So is the statement true or false?
False.
So you can unmute and answer.
False.
Why do you say so?
It has 3 terminals, collector, base, emitter.
What does BJT stand for?
Bipolar junction
The
transistor.
voice is very feeble. Can you please
Uh,
increase the?
Bipolar junction transistor.
Okay. So it is bipolar junction, transistor. So what I am interested in, I want to know the meaning of each terms, right? What does bipolar signify? What does junction signify? And what does transistor signify? So you should be understanding each of the nomenclature, right?
Bipolar means it goes by two ways, by going in and coming out. Junction means it meets in between the circuit. And transistor means that the circuit or device would can work as an amplifier or a switch.
Not exactly. So this is the gap that I am trying to bridge, right? So what you have read in the some of the UG books, maybe not so much reputed books, and that's why there is a certain mismatch in the concepts. So bipolar has two terms, right? Bi and polar. So bi means two, and polar means polarity, right? So bipolar, the term bipolar came from the concept that in BJTs, both types of carriers take part into conduction. What are the types of carriers in semiconductors? Charge carriers. What are the charge carriers in semiconductors?
Electrons and charge carrier and holes.
Electrons and holes. So in BJTs, both types of carriers take part into conduction. While in case of your MOSFETs, for example, only one type of carrier takes part into conduction. So that is why that is an unipolar device. So by the way, what is hole? Anyone wish to volunteer? So what is hole in a semiconductor? We are familiar with electrons in metals, right?
So it is the absence of electron.
How do they that take part into conduction in semiconductors?
Sir, when
It is absence of
electrons,
electrons, but electron
yeah,
takes part into conduction, right? How come an absence of electron will take part into conduction?
when sir, uh, when trivalent impurities makes the holes and
No, no.
through yeah.
Let us not go into this doped semiconductors. Even for intrinsic silicon, right? If you do not dope with p type or n type, there also we see the presence of electrons and holes. So the question is, where does these holes come from, and how does this how do this take part into conduction?
So basically, electrons is only taking part in the conduction. The holes
Okay.
which are there, the electrons fills that holes, and basically uh, the- uh, at at one point hole go to next point, and that electrons place remains whole.
So
That
my
meaning,
counter
yeah.
question would be, why does the same thing not happen in metal?
Sorry, sir.
So anyone
I
else?
think
So if you see the atomic density of metals, and or for that matter to any any your atom would be atomic density of any element would be around 10 raised to 22 centimeter cube. Okay, for metals, if you consider at room temperature, so your carrier concentration or free electron concentration is around 10 raised to 22. What does that mean? That means that one atom contributes to one electron. Okay, so that means there is so much flood of electron in the metal for at room temperature. Now, if you take semiconductors, can anyone tell me at room temperature what is the intrinsic carrier concentration of silicon? free carrier concentration is around 10 raised to 10, right? It is 1.5 times 10 raised to 10 per centimeter cube for silicon. So you see there is a huge gap between the what your metal sees as free carriers and your semiconductor sees as free carriers. So in semiconductor, what happens? You have this 4 valency at your outer orbit, and if you have 4 covalent bonds, right? So let's say, and if you are having a non-zero Kelvin temperature, so some of the bonds break. Okay, so these bonds are shared between 2 electrons. So one electron will get roaming around in the silicon crystal, and it leaves a vacant space, what you are calling it as a hole, right? So how does this vacant place moves? This vacant place move in a way that, let's say, from this bond another electron will come and fill this vacant space left by the earlier electron, and then this hole will be transported to creating a vacant space in the adjacent silicon atom, right? So why does it happen? In case of metal, if you apply some temperature, you know about thermionic emission, right? Your electron, if your applied energy is more than the bounded your bond energy, then that electron will emit, and it will be treated as a free electron in the metal. But in case of semiconductor, what happens? In case of semiconductor, for this bond, the second bond, to create an electron hole pair takes more energy than for this electron to jump into the adjacent vacant place. Okay, and in nature we always prefer the least energy path, because that provides me the most stability. That is why in case of silicon, or any for that matter for any semiconductors, at room temperature you will have both presence of holes and electrons. And how does holes move? Holes move in form of movement of the bounded electrons in the covalent bond in case of semiconductor. So that is how hole come into picture as a separate or uh, different carrier than electron in case of semiconductor. Okay, and in say bipolar transistors, both polarity means the sign of the charge that the carrier carries. Electron carries negative charge, hole carries positive charge. So both type of polarity of carriers take part into conduction. We will see how that happens. So that is why it is called bipolar. Fine. So now the junction, if you see the structure of the BJT, by the way, this is not exactly how BJT looks like in real life. This is just for the representation. Okay. So if you see BJT, for example, let us take PNP transistor. Okay. So what do you see immediately? You see the presence of two junctions, right? This is your one junction. This is another junction. So this junction is called your EBJ. This junction is called CBJ. This is called your emitter. This terminal is called your base, and this is your collector. EBJ stands for emitter to base junction, and CBJ stands for collector to base junction. So the theory of bipolar junction, the theory of the theory of BJT is governed by PN junction principles. Even if you see the collector current formula with respect to base voltage, base emitter voltage, and so on, you can directly correlate it with the your PN junction diode theory. Okay, so because that PN junction theory governs the BJT action, So we call this junction. That term junction comes from there. And what is transistor? What is transistor? Transistor is nothing but your transfer resistor. Okay, transfer resistor means transfer of resistance. So how does transfer of resistance happen? Let me just add page. So basically what is happening in your BJT? Let's say this is your PNP. What is the most preferred way to bias the BJT? For example, if I want to use it as an amplifier, I generally apply forward bias. This terminal is forward biased and this terminal is reverse biased, right? The collector base terminal. This is your emitter, this is your base, this is your collector. So this is your reverse bias, this PN junction. What is the resistance if a PN junction diode is forward biased, and what is the resistance if a PN junction diode is reverse biased? In which case the resistance will be more?
Reverse bias.
In case of reverse bias, the resistance will be more, right? For example, let's say if your collector base junction's resistance, or let's say it is called R out, it will be your D times, this is your collector current, this is your emitter current, so D times BCB divided by D times IC. These are partial differentiation, okay? And in this R in will be your D times VBE or VEB divided by your D times IE. So being in forward bias, this has a smaller resistance. And this has a higher resistance. So you can already see that a transfer of resistance from input to output is taking place, right? So that is why it is called a transistor. And what is the primary requirement for a transistor to be called as a transistor? It has to have a 3-terminal, right? If you have a 2-terminal device, and let's say this is your anode and this is your cathode, and the current I is flowing through it. So what will be your resistance? Your resistance will be dVAK divided by Di. So this is how much nonlinear this thing becomes. There is no transfer of resistance. This is just a nonlinear resistance. Okay. So the primary condition is it has to have 3 terminals and some transfer of resistance should be happening. Okay. Now the question is, these transistors can be used, or this transfer of resistances can be used in favor to get the amplification or switching. That is the secondary part. Okay. But the primary action why it is called transistor is because there is a transfer of resistance going on. Fine. Now you know why BJT is called BJT and why BJT is a 3-terminal device. Okay. MOSFET is a 4-terminal device. However, the transistor action in the MOSFET can be controlled by the minimum requirement for the transistor action in the MOSFET is by only 3 terminals. Okay, 2 terminals will be there between which the current is flowing, and another terminal that will be the controlling terminal. In case of MOSFET, it is gate. We'll discuss it in due course of time. So, as rightly pointed out, BJT is a 4-terminal device. This is a wrong statement or false statement. So the second question asks that in a BJT symbol, the arrowhead represents the direction of what? What is the answer?
None of the above.
Current.
Sorry,
Sir, current.
what do you say, so? So these are two BJT symbols, right? Can you tell me what is what? And how do
First
you
one
remember
is
it?
First one is NPN. First one is NPN
First
and
is
second one is
NPN, second one is
PNP.
TLP. So what are the terminals?
The first one, the P is base,
Is base,
N is collector,
which end?
upwards.
This is collector, and this is emitter. So in case of
Same
this,
terminology to to be applicable to second.
so how do you remember this? Does anyone find difficulty in understanding the symbols?
But, and I understand that the current flow, the arrow means the direction of current, but can you once explain the meaning of the symbols once again?
The symbol.
Oh, yes, sir.
So the meaning of the symbol is from a historical point of view. Okay. So what happened? So by the way, can anyone tell me who invented transistor?
William Shockley.
It is a very wrong statement. And anyone else? Was invented
Oh,
in 47. Okay, by Bardeen and Brattain. Okay. Later, the theory was provided by William Shockley. So this transistor was what type of transistor?
is it a thermosetting transistor?
This is called a point contact transistor. Okay. And later, the next step, William Shockley invented BJT, the bipolar junction transistor. So it is a very wrong concept that the first transistor invented was BJT and the inventor was William Shockley, right? The inventors were Bardeen and Brattain, and it was a point contact transistor. And in this context, the IC or integrated circuit was invented by Jack Kilby. Okay, all of them got Nobel prizes because of their invention. However, the first concept of transistor was provided back in 1925 by a fellow called Lilienfeld. He introduced the idea, however, he could not make the physical transistor. Okay, there is a patent. If you understand what patent is, there is a patent by Lilienfeld, John Lilienfeld, who first introduced the transistor. So we are at the 100th year of anniversary of the conceptualization of the transistor. Okay, now coming to the point contact transistor, how that was made. So they took a semiconductor sample. Okay, this is a semiconductor sample. There they put two metal contacts. Okay, they apply bias to this, and they apply some bias to this. What they have seen is that this current, they were able to control by varying this bias, okay, this voltage. So that is the first demonstration of physical transistor. We call it point contact transistor by these fellows Bardeen and Brattain, okay, in Bell Labs. Let's say this is your silicon or germanium, some kind of semiconductor. Now, do you see the resemblance of this with the BJT symbol? So,
Yes, sir.
this is the BJT symbol, right? So, why this is called base? Because it was used as a base to create the point contact transistor, okay? So, this was called base because of this historical reason. This was called emitter because this was emitting the carriers into the base, and this was called collector because the carriers were collected at this terminal, and that's why the current swing were getting read at the output. Okay, this is how the historically the transistor symbol came into being. Now, how do you remember the symbol configuration? So now if you just rotate it clockwise 90 degree, you will see, or anti-clockwise 90 degree, you will see this kind of structure, right? Now you understand that. And how does your diode look like? This is the symbol of your PN diode, right? So if I can just convert this to an arrow, so this becomes my PN diode. So now, if this is the direction of your arrow, so you understand one thing, that this terminal will be P and this terminal will be your N. Similarly, here this terminal will be P and this terminal will be your N. And you already know what terminal is base. The vertical dimension terminal is base. You already got your other terminal, right? And the terminal carrying the arrow is nothing but your emitter. This is your base, this is your collector. Emitter, base, collector. So now is it okay?
Yes, sir.
Okay, so you can remember it in this way. But if you are comfortable by remembering it by just looking at the component, that is also fine. But this is historically how the symbol came into being. And obviously the direction of the current, this shows the direction of the current. Because in case, for example, in case of PNP transistor, this is your direction of IE, this is the direction of IB, and this is the direction of IC. And similarly, in case of this is the direction of IE, this is IC, and this is IB. So the arrow also aligns with the direction of the current. That is was asked in the question. The reason for this is, if you see in this diagram, you have a PN junction. This is your PNP. Now, in P type, you will have holes as your majority carrier. Now, when you apply forward bias in this emitter to base junction, This holes will move to this direction, right? When holes will move to this direction, in what direction current will flow? Current will also flow in this direction. So that is why in case of PNP, the emitter current is inwards. Okay. And similarly for NPN transistor, electrons will flow, so the current will be flowing the opposite direction. And that is why this is flowing out of the emitter terminal in case of NPN transistor. So let's go to the third question. So can we
Sir,
use, yeah,
oh, sorry, last question about the PNP and NPN. This
sure.
might sound silly, but then sometimes I don't, this question always comes to me when I'm studying these. So when do we know which one we should use though?
When do you know what to use?
Yeah, yes, sir.
In
Because
that
they are like,
depends on what kind of usage you want to have. What do you want to use it for?
um,
Amplifier, switch, what do you want to use it for?
like generally when we're using it on circuits,
Sorry?
when we're and when we're doing experiments, we have to sometimes we have to told to use this transistor or this one. Sometimes I get confused when we get to, when we should know when to use which one.
As long as you use the biasing correctly, the NPN and PNP transistors, the biasing, how do you do the biasing? Depending upon the mode of operation, you either forward bias or reverse bias the emitter base or base collector terminal, right? So as long as you do that correctly, there is no harm. You can use any in your experiment. But if you want to make certain kind of complementary switches and all or complementary devices, then you need to use both NPN and PNP both. Also, in another distinguishing between them is in case of NPN transistors, the carrier which are flowing primary or majority carriers are electrons that are flowing. So electrons will have a higher mobility than your holes. So your NPN transistor will be a little faster than your PNP, right?
Yes, sir.
So holes basically you understand, right? Holes means this this bond has to break. This bond has to break. So that takes a higher energy, or how do you say? For this vacant space to move around the crystal, will take a we will see higher abstractions than a free electron that is moving around the crystal. Okay, so that is why NPN is a little bit faster than PNP. So for your lab purposes, it does not matter whether you use PNP or NPN transistors, as long as you bias them correctly for the intended mode of operation or use. So moving on, the third statement is MOSFET can be used as a switch in both analog and digital applications. So is the statement true or false?
True.
Why do you say so? What is an analog switch and what is a digital switch? Firstly, you are right that the answer is true, but you need to tell me now what is an analog switch and what is a digital switch. So why did you say it is true?
Sir, BJT can be used as switch in active mode by forward biasing the emitter base
No, we are
junction and
talking about MOSFETs, and BJT is not used as switch in forward mode. It is used as an amplifier in forward active mode. So anyway, that is a different topic. We'll come that to later. come to that later. But now the question is MOSFETs as a switch. So do you have understanding of MOSFETs? Symbolically, what is a MOSFET? A MOSFET is a device something like this. This is your drain, this is your source, this is your gate. This is an NMOS. This is gate, this is drain, this is source. So this is your PMOS. Okay. And the structure of MOSFET is again the same thing. N, P, N. But this, there is some additional things. This is your gate, this is your drain, and this is your source. Right? So if you see this region is similar to your NPN transistor, right? This is your NMOS. Okay. And by the way, MOSFET can have also another terminal called body. Now tell me what is a switch. Similarly, for if it is to be a PMOS, so this will be N, this will be P plus, this will be P plus. Okay. So what is a switch, by the way? Let's start from very basic. What is a switch? What is an electrical switch? Which you use to operate your light bulbs and fans. Anyone? What is a switch?
Sir, when the switch is in operation, then the number is equivalent to 1 and then it operates. And when the switch is opened, then the entire circuit does not operate and the digit,
That is
which
the
is
operation of a switch, right? So what is a switch? When you start your statement with switch does this, switch does that, that means you already know switch, but we want to define what is a switch. Switch means a device that transitions between minimum two states, right?
yes, sir.
Either on off or on one, on two, or multiple levels, right? So what is this? This is called as, this is a switch basically. Let's say this is your on and this is your off connection. Okay.
Yes, sir.
So let's say you have something like this. So this fellow is called the pole. This fellow is called the probe. Okay. And this is called a SPST switch. SPST stands for single pole, single probe. Okay. That means when the connection is made, as you have rightly said, it will be on or 1 in case of digital, or in the other case, it will be off when the connection is broken, right? Then there are other kinds of switches. Let's say this is on 1, this is on 2. That means this or that. So this is called SPDT switches, a SPDT switch, or single pole double throw, right? Similarly, you can have SPNT switches, means single pole in number of throws, or you can have double pole single throw also, but those are very rarely used. And if you see the bedside switches in your, if in your bedroom, if you have a tube light and that had two switches, one at your electrical board, another adjacent to your bed, you must have seen that you can control the same throw by two poles or two switches, right? So that is kind of an example of a double pole single throw switch. Okay, so how does MOSFET becomes a switch? So basically MOSFET has to do something. By the way, what is the difference between on state and off state? In which state the resistance will be more?
In off state,
Off state,
resistance will
state
be
is generally called lower resistance state. Off state is called high resistive state. Okay, so let us understand this thing. Now, if we come to MOSFETs, let's say this is my MOSFET, right? This is gate, this is drain, and this is source. So we will study this MOSFET thing in a very great detail at a later lecture. So now, for example, if you know that if your VGS is greater than your VTH or your threshold voltage, let's say some voltage for you now it is some voltage, then my MOSFET is on. Okay, that means what? For example, so we are now dealing with NMOS. So the same concepts apply for PMOS as well. So for example, this is your MOSFET, okay? This is your P type, and let's say this is the oxide, and this is your metal or gate. This is your drain, let's say this is your source. Fine. Now tell me one thing. What do I see? What do I see here? This is a metal, this is some insulator, and this is another material, right? So this is a metal, this is some semiconductor, this is, and between them there is some insulator. What does this remind you of?
capacitor.
So this is a capacitor, right? So now let's say if you have applied some voltage greater than 0, means some positive voltage at this plate, what will happen here at the semiconductor?
Negative charge will be there.
Negative charges should have. Why do you need to have negative charges? Because for a capacitor, if you have to have positive charges, these positive charges transmit electric field, right? These electric fields have to have terminated at a single place. So this will induce what? This will induce negative charges at the opposite side. Fine. Otherwise, for a single positive charge, how does the electric field lines look like? Electric field will be isotropically radiating from this, and it will be where this field lines will be terminated. It will be terminated at infinity, assuming that at infinity there will be some negative charges, right? But in case of when your device is present or a semiconductor is present, semiconductors have both electrons and holes, and also if it is a p type, it also have acceptor ions, that is also negative charge, right? So there will be a region, if you have positive charges here, to cater for that, there will be a region where these negative charges will start to build up. Okay, so much so that some portion of this p type will be inverted to this region, will behave like n type. Okay, now what do you have? Now you have a region. Now if I take this region, what do I see? I see a n plus region, then I see a narrow bridge of n type that is induced by the gate or the controlling terminal, and I see another n type region. So ideally what I have made? I have made a low resistance path between the drain and source, right? Or two water bowls are now connected through a pipe through which the water can flow or the carriers can flow. So now this is the low resistive state or on state. So if I apply some signal here, so the electrons can travel to this and I can get the signal here, output here, right? So this is the switch operation. Now think that I did not have in the off state what I was having. I was having a p type bridge. Then whatever I was supplying here, due to a large potential barrier at these two regions, or in other sense, if you start to inject electrons into it, no, it has too many number of holes. So electron and holes will get recombined. So no electron will reach out to source terminal. So whatever signal you apply here, at output you will get nothing. So this is your off state. This is your on state. Okay. So in the circuital term, what is happening? If VGS is greater than VTH or some threshold voltage, for example, so whatever this signal is coming here, you will get an output signal exactly like this. And if your VGS is less than VTH, so whatever you give here, you get nothing. So this is your off state and this is your on state. So this is how an analog switch behaves. Okay. This is an analog switch. Now, what is a digital switch? What is the simplest example of digital switch you can think of? Anyone?
Not get.
Exactly. That is inverter, right? Start to use the terminology of inverter rather than a NOT gate. NOT gate is also fine, but more formally we call it as an inverter. Okay? So this is basically one switch. If you apply here 1, then your device will output, you will have an off state, and if you apply here 0, you will have an on state. So how does this inverter look like in terms of MOSFETs? If you have seen, your inverter looks like this.
CMOS.
CMOS means complementary MOS. Complementary means you have the presence of both NMOS and PMOS. This is your PMOS. This is your NMOS. So if anyone is being skeptical about this symbol of this knot, the conventional symbol, this is drawn like this. Okay, this is your PMOS, this is your NMOS, This is your input, this is your output. So this is basically nothing but your NOT gate. Okay. So you already know that MOSFETs can be used as inverters, and inverters are the basic building blocks of all the logic gates you have. Fine. With the same architecture, you will get the NAND gates and NOR gates also. We will come into that in probably in week 6 or 7. We'll analyze the inverter in detail. Okay. But meanwhile, you understand that the difference between digital switches and analog switches. And another distinction is that in here you will use digital signals, and at the output you will get the inverted stuff, right? So the moral of the story is MOSFETs can be used both as analog switches and as digital switches, right? But you need to understand what is an analog switch and what is a digital switch. The operations is quite different, and also the biasing criteria are also different, right? For example, in case of analog switches, when this pipe is on, means when we are at this stage, LRS or on state, what should be the on resistance or the resistance of this pipe? Anyone?
Very low and ideally zero.
Very low, right? On
Yes.
resistance has to be very low. So this, remember that this is your ID and this is your VDS. The voltage applied between these two terminals are the VDS. Now if I ask you that, if I give you the MOSFET ID VDS, why do you think you should bias this? I will give you two options, this place or this place. This is bias 1, this is bias 2. Where is your resistance lower? So what is your R on or on resistance? On resistance will be nothing but your dVDS by dIDS. Now can you, by looking or inspecting from the curve, can you tell me that where should I bias the analog switch? At bias 2 or bias 1? Anyone? So what is the resistance here? What is the slope? The slope of the curve is dID by dVDS, right? What is the slope at this point?
Zero.
So what is the resistance?
Infinite.
Resistance is infinity, right? That means whatever I give around this, whatever signal I give, this signal, whatever I give around the bias, at output, I am getting nothing. So I cannot bias it at the place in the deep saturation region, right? This is the place where your amplifiers are biased, by the way. This is where your amplifiers are biased. But in case of MOSFETs, I need to bias at this location, very close to zero, where my R on is the minimum, or the on resistance is minimum, or the IDVD slope is steepest. Fine. So this is where I bias switches. So bias 2 is preferred for switches. So you need to understand these things. There are certain aspects, because in case of digital switches, you don't consider these stuffs, right? It is just a CMOS inverter. You plot the VTC or voltage transfer characteristics, V in and V out, and you get to see how your input and output are behaving with respect to the digital input that you have provided. But in case of analog switches, you need to consider what is your R on. There is also when depending on the frequency, capacitance will also come into play, right? So, but the MOSFET can be used as both. Okay. So, fine. Let's move on to the next question. So, these questions you must have done, but I am trying to give you a little bit more insight onto the topics. Okay, before we start formally. So, differential output of the difference amplifier is the amplification of what? So, basically, V out is equal to some gain times V1 minus V2. This is the definition of difference amplifier. It amplifies the difference of the voltages, right? So, do you recognize this circuit or this element? What is this element?
Operational amplifier.
This is an op amp, right? So, what is the V out here?
AV times V1 minus V2.
So, the question is framed in a way that you already know what an op amp is and what it does, but you need to understand that op amp is also an difference amplifier, right? Op amp has multiple stages. The input stage is a difference amplifier. Okay, difference amplifier, or different, we call it differential pair. I think in this course also you have a certain topic portion of this course is dedicated to differential pair. That is why I am introducing this stuff. So how does a differential pair look like? This is your V1, this is your V2, and from here you are tapping your output. This is your V out. Will be some function of, when I will analyze this differential pair in detail a few times later, sometimes later, you will see that this circuit is very easy to understand, but you need to have some basics of circuit analysis for this. Okay, so this is your M1, M2. These are the NMOSes, and these are the PMOSes. This connection is called diode connected. We will discuss this in great detail later. Okay, so this stuff is called differential pair. This is used as the first stage of op amp. That is what is used for the final output of the op amp, right? And the later stages, what does it provide? That provides your high frequency stability and it to increase the gain. Okay, multi-stage amplifiers are used to increase the gain. Fine, this is called a differential pair. Okay, and this is at the first stage of the op amp we use this. So difference between the voltage inputs. So this is the last question of the warm-up section. So what is the most preferred configuration of the cascade amplifiers? Anyone must have answered this one.
Sir, is it common emitter?
Why so? See, forget about the days where you just answer and do not explain what why you are answering this, right? See, the philosophy should be your answer may be wrong. That is 100% acceptable. But whatever you are saying should have a backing. It cannot be that I found it in some books or on some online sources. You should understand it before you state it. So if it is common emitter, you should tell me why it is common emitter. Any guesses? I know that you must not have, might not have gone into great depth of these things, but that is fine. Just try to answer, right? In that way, also we learn. So, first thing what we are noticing from the question is that we have three types of configuration mentioned here: common base, common emitter, and common collector. We'll go into this in great detail in future lectures, that why it is called common. Okay, let me just tell you, right? So, do you understand the concept of terminals and ports? Have you gone through two-port networks? Anyone who does not know two-port networks? So let me just post one question. What is the minimum number of terminal to create a two-port network?
3.
Why do you say so? Why not 4? Because one terminal can be taken common, right? You need
Common
to
bit.
have one reference.
Yeah.
That reference shall be one, and based on that you can create multiple number of ports. So for a two-port network, you need to have minimum 3 terminals. Okay. Now the terminal, this is input, this is output. The terminal that is common between the input and output is called the common terminal, right? Fine. Now in case of BJT, how many terminals you have? You have base, you have emitter, you have collector, right? Now if I copy this, so what should be your, forget about remembering the stuffs, okay? That study is very logical if you understand it. So what is the common emitter? Let's say common emitter. What will be common between the input and output? So firstly we need to find out the two ports, okay? So if I just make this one common and apply my input at this side and output at this side, this is my output, this is my input. So this becomes my common emitter, right? And what about common collector? What should be common between input and output? So again the same thing. I need to have my collector as the common terminal. So this will be my output and this will be my input. So this is nothing but my common collector. And what is the common base? My base terminal has to be common between input and output. So this is my output terminal and this is my input terminal, right? Now you change the orientation, 90 degree, 180 degree, it is your wish, right? But the common emitter, common base and common collector is very easy to understand, the configuration I am talking about. Okay. Now the question is, what configuration we should use for cascading? So what is cascading? First thing is, what is cascading? Anyone?
Connecting the output of one stage to another stage.
Not good enough. Try again.
Output of one amplifier is connected to the input of the next.
Cascading has nothing to do with amplifiers, right? You see, the concept of cascade should not first introduced to you at the analog circuits course. It should be introduced to you at the network theory course. So what is cascade? You need to at least have two ports. First thing, do you agree or not? Then the next thing is, the input port of the next stage should be connected to the output port of the previous stage. Right? So this configuration is called cascade configuration. Now this stage can be anything. This stage can be resistive network. This stage can be amplifiers, anything, right? Okay. So this configuration is called cascade configuration. Fine. Now the question is that this was cascade. Now what is cascade amplifiers? So cascade we understood. Now what is, now the next question would be, what are the desired characteristics of an ideal amplifier? Anyone? So firstly, why we use amplifier for?
Amplifying the signals.
Is fine. That means we
to
need to have
increase
some
the
gain,
signal
right?
strength.
We need to have some gain, right?
Yeah, yes.
So for ideal amplifier, what should be the gain?
High
What do we
gain.
want?
As high as
Gain is,
possible.
so that is what? For example, you want to make money. How much money you want to make? What is that
Infinite,
number? Exactly.
infinite gain. Infinite gain.
Infinite gain. Then only will that suffice?
High input impedance. Infinite input impedance.
Infinite input impedance. What about output impedance?
0.
Zero output impedance. So guys, I would request you to please carefully watch this part. This is this will break some of the misconceptions you must have. Okay. Other one is your infinite bandwidth. Okay. Then your amplifier has to be stable. Okay. There are other criteria as well. So what we will focus today? We'll focus mainly on these three parts, based on which we'll make our judgment on if cascading is good for and what stage is good for cascading. Okay. Now, is this statement true always? What do you think?
No, it can be low zero input impedance and infinite output impedance as well, because we know from the definition of transistor there should be transfer of resistance, so it can be from 0 to infinity or infinity to 0.
Very nicely put. But you need to tell me in which case of amplifier we should have this. Okay, that is a very good answer, but there is some other aspects to it. Okay, does anyone know about loading effect? Anyone? What is loading effect? This is one of the very important aspect of cascade amplifiers or multi-stage amplifiers. Okay, what is loading effect? Let's say this is your first stage. Okay, and this is your second stage. So this is R, this is R, this is R, this is R. Let's say this is Vx1, this is V out, this is Vx. Let's say let's make this one V2. Let's this is V is V in. Okay. So what is the gain of the first stage? Vx1 by V in. What is that? What is the gain of the first stage? It is a simple resistance divider, right?
Zero 0.5.
So it is half, right?
Half.
What is the gain of this stage? V out of Vx2.
That is also half.
It is also half. So what do I want if I cascade these two? What is the ideal gain when if I cascade these two? By the way, these types of devices are used with your hybrid two-port parameters. Okay. Please revise your network theory courses to get more input about these your H parameters look like. How is it defined? Okay. But what is the gain of if I want to make the cascade stage? The gain should be
1/4.
half times half equal to 1/4, right? This is the ideal thing we want. Now,
Yes.
let me make this connection. This is, let's say, your Vx. This is your V in. This is your V out. What is the gain now? All are R. What is the gain now? because this is ultimately where you will make the cascading, right? What is the gain now?
One
Calculate quickly and tell me.
1/4.
Is it so? Anyone? Come on, this is just a resistive divider, right? What is V out by V in? Come on, guys. So this is what? So this will be what? So resistance, this resistance, this resistance. This is your 2R, right? This is your R, this is your R. So now if you simplify this, what will be this? This is 2 by 3R, this is R. So what will be your V out? It will be what? 2 by 3 by 3 plus 1. That is 2 by 5. So this is now 2 by 5. Where in case of earlier it was what? Is it correct? Is it correct? Anyone? Can anyone not confirm?
Yes, sir, it will be 2 by 5.
Are you sure?
But I still believe, sir, it will be 1/4 because the circuit from upper side is the same that you have drawn in the second case. If we are connect,
Now tell me. It will be the same. Your opinion. That is where the loading effect come into picture. Okay. So now 1 by 5 is clear. I was just making sure that everyone is paying attention. So it seems that nobody is paying attention. So is it now clear that V out by V in is 1 by 5? This is simple resistance divider, right? what is happening. Earlier the gain was 1 by 5, 1 by, now the gain is 1 by 5. So by connecting the two stages, my overall gain is reduced, right? This is called loading effect. That means what? So this circuit, this part is your load stage, this is your load stage, and this was the remaining part is your previous stage, right? When previous stage was at silos or independent, what was the gain? The gain was 1 by 2. That means the potential at Vx1, it was 1 by 2. Now we have that potential 2 by 5. That means the Vx potential at this node, the potential at this node has dropped. Why it is dropped? Because some part of the current is sucked out by the load stage. Okay, this is called the loading effect. It will ruin your device if you don't pay attention to this particular effect in cascade stages. Okay, so what is happening basically? Earlier, let's say this was your load stage, right? But this was not connected to the input stage. This was not connected here. That means equivalent to what? Equivalent to you have a resistance. Now you had, instead of 2R, earlier you had infinite resistance, right? An open circuit is nothing but an infinite resistance. You see? So instead of 2R, here you see, right? It is 2R. The load stage was providing you a series combination of R and R, that is 2R. So that 2R resistance was draining some current out of the Vx node. But when these two stages are different, the first stage was seeing an infinite input impedance of the next stage. Fine, this impedance was infinite in the first case. That is why this first stage gain was 1 by 2. Whereas in this case, Vx, if you do Vx by, this is nothing but Vx by V in, right? So you would see that the first stage gain has dropped because of the second stage or the load. This is called the loading effect. So how do you get rid of it? If you have a mechanism, where you had this stage, right? If you have a mechanism, this is your V out, this is your V in, where this will see, let's say I am connecting something here, okay? I am connecting just two port, I am connecting some network here, which gives me what? Which gives me gain of 1. So what? So that this Vx node translates to directly Vx at this point. Gain of 1 means this voltage will be directly multiplied by 1 at the output of the network, green network, and it will give me 1, right? It will give me Vx. But however, if I can make something like that, the input resistance looking into this is infinity, right? And the output resistance looking into this is 0. That means what? That means by this Vx will remain intact for both the stages. What you by default assume when you are analyzing this circuit, right? some person was telling me that it has to be the same thing as earlier, but there you have assumed that these cases are intact, that your R in is infinity and R out is 0. So this element, this element is called nothing but a voltage buffer. It is nothing but an amplifier with a gain of 1, which have very high input impedance and very low output impedance. Okay, so in that way you can prevent the loading effect. Is that clear?
Yes, sir.
So in cascading, what do you want? We want the stages should have high input impedance and low output impedance, but there is a caveat. Basically, we want high input impedance and high input impedance and low output impedance. Is this statement always true? As somebody has pointed out, this is not always true. The reason behind that is this is true for only voltage amplifiers. You guys know about dependent sources? Current control current source, voltage control voltage source. You guys are aware of
Yes,
that?
sir.
Okay.
Yes, sir.
So first thing, tell me how does an ideal voltage source look like? So a general voltage source will look like this, right? Vs and this Rs. What is Rs? The series resistance of a voltage source. That is nothing but your Thevenin voltage source as well. You can consider it in this way also. When you use your Thevenin's theorem, you connect a voltage source in series with a Thevenin resistance, right? That is the same concept for any general voltage source. For an ideal voltage source, Rs should be 0. Similarly, if it is a current source, what should be the Rs for an ideal current source?
Infinite.
Rs should be infinite, right? For ideal current source. Now, if this much is clear to you, now let us go into voltage amplifiers. Voltage amplifiers. How is it is defined? V out is some A times AV times V in, right? So what is the circuit representation of that? Circuit representation is this is your V in, and somewhere far you have a voltage source that has the voltage of A times V in, and this is nothing but your output. Is this part clear? This is the sub-circuit representation of an voltage amplifier.
Yes, sir.
Fine. Now, by definition, you will have some resistances. This we call R out, the output resistance, which I want to get the ideal voltage amplification, right? For that, what do I need to have my R out to be in this case? I want my voltage source to be ideal. So my R out, I want to have 0.
Yes.
Understood? And this is only true when my amplifier is a VCVS or voltage controlled voltage source. Fine. Now, what about your devices? For example, I can have transconductance amplifier as well. Transconductance amplifier. What is that? That is nothing but my MOSFET. For example, V out is nothing but GM times V in. This is GM is called transconductance gain. ID is nothing but the GM times VGS. Okay. That means what? In case of MOSFET, if this is my gate, this is my source, then I have a current source, GM VGS. This is my VGS, right? This is the common source amplifier. You see the source terminal is common between the input and output. This is your input, this is your output, right? So for a transconductance amplifier, what do I have at the output? I have a current source. I have a current source. So that current source should have a non-ideality. That is what? It should have a resistance as well. This R out. Now, in case of transconductance amplifiers, what R out you should want to be? Or what you want your R out to be?
0.
If it is 0, then it is a short circuit, right? You see the same definition from the ideal current source. I want a current source. In parallel, I have a resistance. If my resistance is short, then I have nothing. These two terminals are connected, right?
Yes, sir.
So, see, okay. So, for example, I have a current source in parallel with a resistance. This is my practical current source, right? I want to have a ideal current source. What should be my R out? What should be R naught? From this to this?
Infinite.
No, you don't answer. The doubt is who had the doubt? I think Molly Chopra, you had the doubt, right?
Yes, sir, I had that.
So
Yes, sir.
now tell me, what should be R naught from left circuit to right circuit?
Sir, it should be infinity.
Why? Because I don't want this, right?
Yes, sir.
I want
Because
this circuit to be open circuited. Open circuited resistance is what? Infinity, right?
infinity. Yes, sir.
The same thing I want at my transconductance amplifier. I don't want this R out to bug my device or to get a lower value of current source, because if I have R out, no, this both current will flow into the both branches. But I don't want that. I want all my current to flow into this control source, so that I can just use a load resistance and bring out this as an amplification, right?
So, sir, this R won't be 0 because it would get short circuit. So, may you
The
please?
same concept is applying here as well, right?
Okay, sir.
If you apply your R naught as a R naught equal to 0, your R
Yes, sir.
naught is 0, then this is short, right? When it is short, then current source does not matter.
Yes, sir. Okay, sir.
That means the output voltage, what is the voltage? What is the voltage across the short? What is the voltage across the short?
0 volt.
0, right? So whatever you give at your input, you will get nothing at your output, right?
Yes, sir.
So around R0 is not permissible at all. So that is why you need to have an open. And in other word, in case of a transconductance amplifier, your R out has to be infinity. And this is what? This is your VCCS, voltage control current source, this transconductance amplifier. The way your MOSFETs and BJT works, mostly as a output is as a current source, because ultimately you are controlling the drain current or the collector current in virtues in reference to your gate to source voltage or base to emitter voltage. So that is why your transconductance amplifier, where the output is current, input is voltage, your output resistance has to be infinity. So the statements we had made earlier, no, these are not always true, right? These are true only in case of voltage amplifiers or VCVS, voltage controlled voltage sources. Please remember this point. So whenever you are asked what are the characteristics of an ideal amplifier, you should always start the answer by assuming that your amplifier is a voltage to voltage amplifier. Okay? Not transconductance amplifier, not current to current amplifier, right? Not voltage to current amplifier. Is that clear? So whenever you read stuff, no, there is much more into it. What is been told to us in your undergrad studies. So I am trying to bridge those gaps. Okay. So feel free to ask any questions, whatever you don't understand. We can go much deeper to the extent I know. Beyond that, I cannot answer. Is that okay? Okay. I think I made the point that these statements are needed to be taken care of very carefully. And okay, so I think we can start this part. Uh, um, yeah, I think we can start this part from next. This will be better. This will be a continuation of. I think that will be all for today. Please ask me if you have any questions. Else we will conclude this. So on the topics what we have discussed, or if you are facing any difficulty in answering the assignments, you can ask that as well. I will not give you the actual answers, but we can discuss. Any concepts you don't, you are finding it difficult. So if not, then let's call it a day, and let's meet you at next Saturday with some interesting assignment problems, and hopefully you will have more questions for me. Okay. So thank you everyone. Please do revise the lecture whatever is posted on the this SWAYAM portal, or also if you can if you want to brush up some of the concepts I have discussed today. This will be posted on a YouTube channel. That link will be shared to you by the NPTEL. Okay?
Sir, the session on 29th, is it a continuation of this or more questions?
On 29, I am not aware of anything on 29. Is it Saturday? 29? I don't think so.
Sir, actually, when we got a link for this session, they mentioned two sessions. Session 1, that is today. Session 2, which is on 29th. So, is this like a repetition class or continuation class?
See, my session would be on every Saturday. Okay. I don't think there are other TS for this course, but I am not sure. So I will see my mails as well. I have to enroll for the course as well, but I don't see any 29th of deadline. I think your assignment one is due by 6th of August, right?
Yes, sir.
Okay. So before that, I cannot discuss your assignment. 29th, I am not aware. But my session, whatever is on next Saturday, will be a continuation of this. Okay, we'll build upon whatever we have discussed today, and we'll go into progress the course very slowly, so that you understand. Right?
Yes, sir.
Thank you.